Good evening, sir.
Yeah, and audible clear?
Yes, sir.
Thank you. Yeah, so we'll start the session. Okay, so good evening. My name is Rohit. I'm a PhD camp student at IIT Madras in the Aerospace Department. And so, welcome to the course on fundamentals of combustion. So, this is a weekly session. So, you will be having each Saturdays we will be having this session, and we'll deal with. So, it's a 2 hour session. So, since it's a 2 hour, first hour I will try to briefly explain what throughout the last week what professor has sent you the videos or what you have been asked to watch, and in the next and the second 1 hour I will try to solve some of the questions so that it will help you in solving your assignments, and if you guys have any questions or anything, we can discuss later. So I hope that's clear. So yeah, so in the course of fundamentals of combustion, the major objective of the course is to get knowledge of the thermodynamics of combustion and apply those concepts. And so brief outline of the course, it includes basics of fuels you will be taught, then you have stoichiometry conditions, then you will be taught about chemical kinetics and equilibrium, then mass transfer and different types of combustion processes, and then mathematics involved with this. So each sessions will try to cover each of it. And so today we will be trying to go with week 1 and week 2 sessions. Eventually week 2 you will be dealing more with first law and second law things. So in week 1 you have been sent videos on fuels and their properties and review of basic thermodynamics of ideal gas mixtures and stoichiometry related videos were sent. I think it was the first and second video, first video that was there for week 1. Then you have first and second law of thermodynamics applied to combustion. So these are the major broad areas that were covered in week 1. So in the first 1 hour, I'll try to give an overview of what was there in week 1's videos, and in the second 1 hour, we will try to solve some problems. Is that okay, or you have any questions on it? Okay. So we'll begin with week 1. So the first topic that was dealt was on fuels and their properties. So these videos will be recorded and will be shared to you.
Yes, sir. Thank you, sir.
Yeah, so you will be getting mails regarding the link of an Excel sheet where you will be having the video links of this particular session, and you'll be having the link for the PDFs and all the materials that we are discussing here. So we will start with fuels and their properties. So the major thing that we dealt in week 1 was the term called combustion. And you know, combustion reaction is an exothermic oxidation reaction. So this is the first thing that we learned in the lecture, that it's an exothermic oxidation reaction. And so we saw there were, so by the term fuels, in our case we mean is it can be an hydrocarbon or any hydrogen fuel or methane and say on. Yeah. So in an hydrocarbon fuel you will be having the carbon atom in the fuel, and it should be oxidized by O2 that is present, which is present usually in our case O2 will be present in our air itself. So we will be using that O2 from the air, and we will be using the hydrocarbons. So we have fuel, so which has these hydrocarbons. So with this O2, they will form different forms of carbon dioxide, and you can form H2O. So these are the different output products of the combustion that we get. And with these output products, you will have certain amount of heat release. That is, heat is released to the ambient. So this heat release, since it's released out, you call this reaction as an exothermic reaction. So you have an oxidation going on and you have an exothermic reaction. So these two are the major characteristics of a combustion reaction. And the major products of a combustion reaction involves carbon dioxide and water, that is H2O. Then combustion reaction predominantly takes place in the gaseous state. That is the second point that you need to be remember. So this is the second thing. So it should be in a gaseous state, because even though there are surface reaction in solid fuels, most of the reactions that we will be doing is related to the gaseous state. So you have the fuel vapors and you have oxygen in the gaseous state, and they combine. When you are giving the required spark or ignition you will get the combustion within the system. So that's the overall idea that we work on. So towards the end we will see how a carbon charcoal or a coal, how it burns. That's a little bit different, but at the initial stages we will go with gaseous state combustion. So therefore fuels in gaseous state, they readily mix with air and react. So that's the characteristic why gaseous fuels or with oxidizers are used. Our liquid and solid fuels have to be first gasified. So I will just write it here. If you have liquid or solid fuel, they need to be first vaporized. So this is a requirement of our combustion system. So if you have a combustion system and if you have a liquid fuel or a solid fuel in your hand, the first thing that comes to your priority is you need to be properly vaporizing it, so that and with sufficient amount of air you can get the required reaction. So that is the second thing that you have learned in the video. Then we dealt with different types of fuels. So the third important thing that was taught was different types of fuels. So majorly there were two things. One is fossil fuels and the other one was synthetic fuels. So that is the fossil fuels, they are formed over several years through geological processes, and later they are, so this one is a man-made, this is formed from geological process. So if you have any questions or anything, you can just stop me and ask. So different examples of fossil fuels, if you see, you have petroleum, crude oil, etc. Some of them are discussed in the lectures. And then you have synthetic fuels, where the examples like biogas is one major example. Then you have biodiesel, synthetic gas, and all this. So as fuel, the one of the major property the fuel should be having is it should be having a high calorific value. So or what we call the heating value. So this is the third important thing that you need to consider. So what calorific value means, and this definition is important. So it is the amount of heat released in an exothermic reaction when 1 kilogram of the fuel burns completely with sufficient amount of air required for its combustion, and the products are cooled to 298 Kelvin. So that is 298 Kelvin is nothing but your standard reference temperature. So that's the definition, and it's better you understand this definition. So what it says is, it says the amount of heat released. So it is the amount of heat released during the exothermic reaction when 1 kilogram of fuel burns completely with sufficient amount of oxygen. So sufficient in the sense, you might have heard in the video saying stoichiometric equations and all. So that's what you mean by sufficient amount of air for complete combustion. So with sufficient amount of air, you will get combustion products as the outlet. But this is not enough. Your combustion products needs to be cooled to 298 Kelvin. So this total process involves certain amount of heat that is being released. So that's what we call as, so that's the amount of heat that is required is what we call as calorific value or the heating value of the fuel. So in gaseous fuels, one of the important characteristic of the gaseous fuels, they are cleaner, and whereas liquids and solids you can have very minute particles being present in the liquids and all. Then we use different filters. That's what, if you have heard about filters, when you're using a liquid fuel and all, you need certain filters to remove small particles which are present inside the liquid. These are not purposefully done, but these are particles that come through when you are through your refining process or some arguments. So that's about gaseous fuels. And but gaseous fuels, they have a low density. Their energy density is also low. So since energy density and they have a low density, storing them is a difficult task. So gaseous states have low density. So storage requires a huge space. But space is very constrained for us if you are considering rocket engines or a gas turbine engines that are used in airplanes or any system. We need to make the system as compact as possible. So you can't allow for storing the gaseous fuels in such huge spaces. So most of them, what we do is we use a compressed storage in pressure vessels with proper regulators. So you can compress your gaseous fuels to liquid state, because now liquids have a higher density. You can store it in a much smaller space, and by using a proper regulators, you can convert the liquid to gaseous form and do the required combustion. So that's the total idea in practical systems, where you might have seen the autos or they have a cylinder at the back of them. So they are all having, similarly the LPGs that you have in your home household, they are all liquefied, and so that they are stored at, you can store sufficient amount. So once said that, there are different gases available. So the first one that you had dealt was related to natural gas, where you have mostly the methane content in present in it. Then you were taught something called LPG, which is called liquefied petroleum gas, which involves blends of several hydrocarbons. Majority includes butane and propane. Content will be the maximum. And some other components of butene, propene, and UVC. Then you have some other thing called refinery gases. So these are got during the refining of the petrol, and these have further higher hydrocarbon chains and carbon monoxide, hydrogen. These are the components in these refinery gases. Now there are some other types like coal gas, or you have producer gas. These are gases that have some small changes in their composition. So these are derived from the coal and solid fuels. The coal gas, producer gas, and synthetic gas. And another gas that you will be most familiar is something called biogas. This is derived from your animal and plant. Yes. So these are some sources of fuels in the gaseous state. Now, if you look into the one natural gas, so natural gas has a molecular weight of around 16 kilogram per kilomole. So it's nothing but methane. Methane has a unit of 12, and hydrogen has a unit of 1. So 12 plus 4, that is your 16 kilogram per kilomole is what we are seeing. And since it's mostly contains of methane, the calorific value of natural gas ranges from order of say some 50k to 55k kilojoule per kg. At the same time, for LPG, if you compare this thing, so LPG is a blend of different several hydrocarbons, and you have a molecular weight of close to 55 kilogram per kilomole and a calorific value ranging from 45k to 50k. So it's pretty close. But LPG has a molecular weight of close to 55 kilogram per kilomole. So it's a bit more dense compared to the natural gas. So it transforms into a liquid mixture. So LPG is stored at say some 6 bar in the cylinder. Then using your pressure regulators to convert them to gas for your cooking purpose. Then you have your coal gas, producer gas. These are these gases. See, they are different based on their composition. They are named differently. Major components include carbon monoxide, hydrogen, and carbon dioxide are the major components. And you have nitrogen, which are inert gas. So thus their molecular weights and calorific values also vary based on what are the composition percent. So coal gas will have a different molecular weight. Producer gas similarly will have a different composition, so different molecular weights. So one example that you were shown was like the producer gas has close to say 16 to 20% of carbon monoxide. It has 16 to 18% of hydrogen and 8 to 10% of carbon dioxide and some traces of nitrogen and other hydrocarbons. So you need to consider only 20% carbon dioxide when you are calculating the molecular weight for producer gas. And another fuel, that is the biogas, which it also contains 60 to 80% of methane, that is CO2, and it has 20 to 40% of carbon dioxide. So these are by volume. When you are saying 80%, so 80% of volume you will be having these particular gases. And one backlog is that you have a calorific value ranging from 30k to 32k kilojoule per kilogram for biogas. Compared to LPG and all, you have a little lesser calorific value. Then, so this was one another thing. And yeah, said that. Are there any questions? Okay. So some other important parameters that were dealt is, one is the density, that we saw how gaseous fuels are having low density. And another important term that we need to remember is something called specific heat. And another one is called thermal conductivity. And based on your system fluid, its viscosity is also. So these are some important gas properties, these fuels which are used for the transport process. So these are some of the things that you need to be aware if you are reading through a gaseous fuel. These are some characteristics of a gaseous fuel and some examples that you need to be reminded of. And if we go to the liquid fuels that were taught to you, so liquid fuels, they have much higher energy density than gaseous fuels, as we know. So because the density is more, so its storage is also simple without requirement of big pressure vessels and all. So liquid has to, one important thing is, as we said, most of the combustion that we are looking at is a gaseous state combustion. So your liquid needs to be converted to the gaseous form. So if you have a liquid fuel in your hand, so you need mechanisms to properly evaporate or vaporize to vapor, and then these vapors participate in the chemical reaction along with the oxygen plus. So while you doing this, the vaporization, what we said, It is dictated by the volatility of the gas, that is how easily it can get into a vapor state. So the volatility is governed by the properties such as the flash point, we have the fire point, and then we have the boiling point. So these are the three characteristics that a liquid fuel when you are using, and it's vaporizing. So these are the three characteristics that governs this vaporization. Among that, so if you look at flash point, in short, if I say flash point of a liquid fuel is nothing but the minimum temperature of the liquid at which sufficient vapors are produced to mix with atmospheric air and produce a flash or an instantaneous flame when a pilot flame is introduced over the liquid surface. So it's like in a flash point, you reach to a particular minimum temperature where you get a flash of flame when an ignition source is given, and when it's taken back, it goes off. The flame, when you're taking back the flame gets disappeared. Whereas in the case of a fire point, it is the temperature. So you will have first flash point. Then, if for a further higher temperature, you see that the temperature higher than the flash point, when you give a ignition source is introduced, a flame sustains over the liquid surface, and even after the removal of the pilot ignition flame. So flash point, the difference between flash and the fire point is when you give an ignition source over the liquid surface, if you get sufficient amount of vapors to get a small flash, and when you remove the source and if it is going off, then it's called a flash point. And the temperature at which you get sufficient vapors such that even if you take back the ignition source, if the flame still persists over the liquid surface, the flame persists over the liquid surface because there are sufficient amount of vapors that are generated from the liquid surface. So that's the point you need to remember. So this particular point is what you call as the fire point flame. So that's what we say about fire point. And the third one is boiling point. So now boiling point is a temperature higher than the fire point, and it is nothing but the saturation temperature. So it is nothing but the saturation temperature of the liquid at a given pressure. So for a given pressure, you have different values of saturation temperature. So let's like water boils at 100 degrees centigrade. So liquids with lower flash point and boiling point, such as gasoline, methanol or heptane and so on, they vaporize much rapidly. So if you have a low flash point and boiling point, so you need to heat your liquid to that much temperature only for getting you the sufficient vapors. So it gets vaporized very fast. That's the catch in that. Now in liquid fuel, though we said converting it to gaseous is it's not so a simple process. From liquid to move to a gaseous form, you need to first make your liquid surface area maximum. For that, you use something called atomization. So you have a chunk of liquid, you atomize it into very smaller droplets, because vaporization is a surface phenomenon. So your surface area is as maximum as possible, you will get maximum vaporization happening. So in atomization process, you have a liquid which is disintegrated into smaller finer droplets, and this particular droplet atomization depends on two major things. One, it depends on the liquid viscosity, how viscous the liquid is. Based on that, you will get the different atomization things. And another one is the surface tension. The surface tension brings the droplets into a circular form, and the surface area that is exposed to getting vaporized and all is depend on your surface tension. Yeah, so said that on liquids, one more important thing that you need to remember is something called latent heat of vaporization. So these terms are important. Since it's a first class, you need to get through these basic steps. So this latent heat of vaporization is nothing but the energy that is required for converting the liquid to its vapor. So there are two things. One is increasing your temperature, that's what you call sensible heat. And latent heat of vaporization is when there is a phase change. From liquid to gas, there is a change in phase. So that energy that is required for converting the liquid to vapor is what we call latent heat of vaporization. So that's what we call. So the energy required to convert from liquid to vapor is what we call latent heat of vaporization. And a higher value of latent heat would indicate that you need higher amount of heat is required for the phase change for a given pressure. And so the liquid fuel is usually at a temperature less than the boiling point, because if you keep your liquids at less than boiling point, else they will start forming gas. And the main problem with this is because say if you have a tank and if you will fill your liquid up to the, if your liquid is at boiling point, then you will start getting vapors all over here, and this will now make the chamber highly pressurized, and the pressure will increase to tremendous values as the vapors are getting more and more. So this will be a problem. So you usually try to keep your liquid fuels at a temperature below the boiling point at the beginning. So you need heat to increase the temperature close to the boiling point. The heat supplied for this process, so the heat that is supplied to heat the liquid to the boiling point is what is being referred as sensible heat. So this is another important term that you need to know. So this depends on the specific heat of the liquid. So then for the phase change, the latent heat is to be supplied. So the volatility of the liquid fuel is generally governed by liquid phase specific heat, boiling point, and the latent heat of vaporizations. So these are some things that you need to remember in the liquid fuels. And if we go on to the examples of liquid fuels, some examples that you were taught is like we have crude oil, which as a whole by weight which consists of some 80 to 85% carbon, and say some 10 to 15% of hydrogen, and some traces of sulfur, oxygen and nitrogen are also being present. So when crude oil is subjected to something called fractional distillation. So fractional distillation is a process where you segregate, you have a distillation column and you segregate different gases according to their densities. You can segregate it out. So this distillation process separates it out different fuels from the crude oil, and you get something like gasoline, kerosene and diesel are the primary components which are used in the automotive or aerospace industries. And there are heavier components than diesel that cannot be used in applications which are further processed. So denser things will be segregated out at the bottom of the distillation process. So they need more finer refining things to be used as a, say, tar or some these kind of things. You need to be doing more and more refining for them to be used in other purposes. And the major things that come out of the things is gasoline that we use, then we have kerosene, and then we have diesel. So these are some other components that are more frequently used by us. And then so apart from these are fossil fuels, and apart from non-fossil liquid fuels like man-made things like the alcohol or liquefied salt, and one another thing is like your vegetable oil. So these are another non-fossil fuels. example of non-fossil fuels. Then in alcohols, you may remember being taught something called ethanol, which is obtained from sources such as sugar cane and corn. And this ethanol, if it is blended with gasoline, it can be used directly in engines as a fuel. So ethanol blended gasoline things are recently been tested for engines and all. And oils extracted from vegetable seeds, such as the rapeseed or sunflower seeds, or these things will have very high viscosity and which are subjected to something called trans-esterification. Trans-esterification is nothing but it is a process in which you have your alcohols, using your alcohol such as methanol or ethanol, you break the chains of hydrocarbons into different forms, and from there you take the alcohol content of that particular liquid and use it as fuel. So that process is what you call trans-esterification. And the processed vegetable oil with much lesser viscosity is what you, the byproduct of this is what you call as biodiesel. So that's one example of non-fossil fuel liquid fuel content. So these are some examples of liquid fuels that we are taught. And if I move on to the another topic that we were taught, something called solid fuels. So solid fuels like liquid fuels had very higher energy density compared to gaseous. Now solid fuels have way higher than the liquid fuels, and but they are a bit complicated than liquid fuels because of their heterogeneity. Because in a particular solid fuel you can have water vapor, you have trapped gases, you have surface burning. Some major example is like you have coal and wood are the common examples, and coal is a naturally processed material got from which are taken from the underground things. And so in a solid fuel, what you need to remember is in a solid fuel there are mainly 4 typical components. Among that, the first one is the moisture, second one is your gaseous substance, which is nothing but your volatiles. Then you have your fixed carbon, which you call choke or char resin. And then you have your mineral content that you see at the final as ash. So these are the main 4 components in a solid fuel. And you use different analysis to determine the fraction of each of them. So some solid fuels, they have a blend of sulfur also in containing them. So the calorific value of a solid fuel depends on its volatility and the percentage of carbon that is present in the solid fuel. So that's one important thing you need to know. And if you see, remember the lecture we did, a table was shown to you with different amounts of carbon percentage. So I will not go detail into those things. And yeah, so are there any questions? Okay. So next thing that you need to notice, so since we said solid fuels and all, some important fuels that are used in space applications. Because as you might have seen, rockets being moving up to with very high intensity of energy and all. So these space applications, they need much more higher energy density fuel. So some of them that is used is something called, first one is called hydrogen, that is N2H4. So the property of hydrogen is that it decomposes by itself exothermically at high temperatures of say 600 degrees centigrade. And so this happens when you have a catalyst made of say iridium or molybdenum. They impinge on this particular hydrogen, and this will decompose hydrogen into gases almost within it. Instantly it will make gases out, and this gases then it comes with contact with the ignition source, and it provides the required energy. So this hydrogen is something called as a monopropylene, because you need only one particular source to propel your engine. So in rockets or gas turbine, in rockets basically, we use these monopropellants. And by propellant, this term is used in rocket theory. We use for fuels we use propellants, where you have a blend of both fuel and oxidizers coming out. So this is called a monopropellant because you need only one hydrogen to get your required combustion. And one another important fuel that is being used is something called unsymmetrical UDMH, which is nothing but unsymmetrical dimethyl hydrazine. So if you see the chemical formula, it is N2H2CH3 twice. So this unsymmetrical dimethyl hydrazine on contact with a small amount of, so this requires some oxidation. So red fuming nitric acid, RFNA, it's called red fuming nitric acid. It produces bright flame and they react in liquid phase, releasing components which react in gaseous phase exochemically within. So this has a order of say some 15 milliseconds. Within 15 milliseconds, you will get the required combustion and high energy will be produced when RFNA combines with this UDMH. And another important fuel that is being used in space industries is liquid hydrogen. This you might have seen in rockets. You might have seen the third stage of GSLV rockets, and where we say it's a cryogenic liquid. So there we use this liquid hydrogen. It's a cryogenic liquid. One important hard thing about cryogenics is the temperature at which you need to store it. So liquid hydrogen you need to store at minus 253 degrees centigrade. So which is close to say 20 Kelvin. And liquid hydrogen is an excellent fuel because once on combination with oxidizer, this will only produce water vapor, H2O is the maximum thing it comes out. And it has very high energy density, high energy value. So you will get more energy from a small, within a given quantity of hydrogen getting combustion. And the outlet products doesn't have any carbon dioxide or anything which can result in pollution and all. So people are trying for liquid hydrogen engines and all these stuffs recently. And there are several other oxidizers that have been discussed in the lectures. So I will reduce my talk to all these stuff. Then, so set these different fuels and their characteristics and some examples we have seen. And then for studying these things, you eventually will start looking at the thermodynamics of the fuels and all the things that you need to know about regarding these fuels. So any equation that represents a relation between the pressure, volume and the temperature is what we usually refer it as equation of state. Now you may be reminding, when we say equation of state, the first thing that comes to is an ideal gas equation. So the ideal gas equation, that is PV equal to nRT or RT here. So here R refers to your specific gas constant. What is the, for a given gas, what is the specific gas constant of that? Which is, its units is in joule per kilogram Kelvin. And V is nothing but your specific volume. And so its unit is in meter cube per kg. And P is your pressure in pascals and T is your temperature in Kelvin. So no real gas will follow this ideal gas law. So real gases have different van der Waals equations and different real gas equations are present. But most real gases behave like an ideal gas at high temperature or low pressure. So in low pressure or high temperature conditions, most of the real gases, they behave as an ideal gas. So in our most of the engineering applications that we look into, we see that this pretty works well because we are dealing with very high temperatures. So you can consider these ideal gas equations for getting an approximate estimation of what is happening, because the combustion products are at high temperatures and in many cases they have much low density and behave like an ideal gas. So So ideal gas is not something that is not useful, but it can give you a pretty good approximation of what is happening in the system. Then, according to the Avogadro's hypothesis, you might have seen in the lecture that 1 kilomole uh, of any gas at standard atmospheric pressure of 1 bar and temperature 273 Kelvin occupies a same volume of 22.416 meter cube. So this, based on this, you will have something like PV is equal to MRT, where M is nothing but your MR is nothing but your universal gas constant. RU is it, and the value is nothing but 8314 joule per kilomole Kelvin. So this value, it's better you get used to this particular value, because sometimes they will be given, sometimes you need to by heart. So from this equation you can see the gas constant is nothing but universal gas constant by the M, where M is your molecular weight of the species. And in terms of universal gas constant, if you write this particular thing, can also be written as PV equal to NRU into T, because weight by molecular weight is nothing but the number of moles. So N is nothing but your number of moles. So for an ideal gas, so there was an experiment by Joule's experiment. So there is a relation between energy, internal energy, and enthalpy. So enthalpy is represented by H, which is under constant pressure. You have internal energy, that is at constant volume, will be H is equal to U plus PV. This PV is nothing but your work done, and this can be again written as U plus NRE into T. So this is one important relation that will be helpful. So you can write this enthalpy in terms of temperature in a polynomial function that you might have seen. And one another important thing is the specific heat at constant volume, that is given by du by dt, and at constant pressure if you take, you will get something called enthalpy of the system. So the difference between Cp minus Cv is what you call specific gas constant R. So these relations are important from the thermodynamic perspective. And said that, now another important thing that was taught to you was regarding the gravimetric and volumetric analysis. So in all these upcoming weeks and all, you will see the mass fraction of, that is, you have a set of different gas mixture under ideal conditions. It can be treated as constituent of different ideal gases, and if you have, say, a mixture of gases, say M is your total gas, which has a mixture of M1, M2 and so on, different gas mixtures you have, say N gas mixtures you have. So the capital N is nothing but your number of components or species in the mixture. So you have a gas and there are different components within it. And say there are N number of components within it. Then the mass fraction. So this particular notation we will use throughout the lecture. In all upcoming lectures you will see this particular notation. So mass fraction is represented by capital Y. So for a ith particular component, mass fraction can be written as the mass of that ith component to the total mass. So this is nothing but your mass fraction. Similarly, the volumetric analysis provides a volume fraction of all individual components present in the mixture. So from that, you might remember from the lecture, so you have different volume fractions of different species, and volume fraction is nothing but is defined as the ratio of volume of given component to the total volume of the mixture, and this volume fraction is equal to, it is nothing but proportional to the mole fraction which are used in the ideal gas equation, that is PV equal to nRT n URT. So when you are saying volume fractions or mole fraction, both are the same thing. So you can write number of moles, that is n is equal to n1 plus n2 and so on for the total mixture. So important thing to notice, the mole fraction will be represented by capital X. For an ith component, mole fraction is nothing but the number of moles of that ith component to the total number of moles in the mixture. So that's one important thing that you need to be remembering. And there were different mixture laws that were taught to you, and if I go a bit faster, then you were taught on something called stoichiometry. So this was the next topic that was started. So you might have seen one particular lecture on that. So stoichiometry is nothing but it's a science used to determine the amount of oxidizer that is required to completely burn 1 kg of a fuel. So that is like to form carbon dioxide and water vapor, which are the major components of a combustion reaction. So stoichiometry relates to that you try to get a complete combustion happening for the given fuel. So it's a theoretical value arrived at as an assumption of complete combustion. So that's the key point here. So it is taking by complete combustion you are assuming, and theoretically you are deriving the maximum amount of air required and all these things. So for this calculation, even for this lecture or upcoming lectures, you will consider air is composed of 21% of oxygen and 79% of nitrogen. These are considered in terms of by volume. This is the percentage constant. And for most of the situations, the impurities such as argon, carbon dioxide, they are usually present in small amounts, so we don't consider those things for your equations. But eventually, when you are going with finding adiabatic flame temperatures more precisely for actual emissions, you need to take into account all these reactions. Usually in a carbon oxidation reactions, if you see the textbooks, you will see that there are hundreds of reactions that are happening between particular given reactions. So you need to take into account if you want more precise understanding of the combustion, what is happening and all. So the important thing or a relative shortcut to remember something is like if you have a general hydrocarbon that is represented by CXHY, which contains X carbon atoms and Y hydrogen atoms. So for a single step reaction, so remember here single step reaction is what we are taking. That is, you don't consider an intermediate all sets of reactions, you are not considering it. So for a single step reaction, considering its complete combustion in air, so you have complete combustion, say some A molecules, A moles of air will have oxidizer, that is O2 plus by volume it is 79%, so it will come to 3.76 times nitrogen content. So this on complete combustion it will produce say X moles of carbon dioxide, and you will get Y by 2 moles of the vapor and 3.76 times A into A times nitrogen. So this is the for a given standard hydrocarbon fuel. These are the output products. And one important relation, if nitrogen is treated as inert, then you can equate different atoms present in the system, both the right hand side and product side and the reactant side. So you will get relation like A is equal to X plus Y by 4. So this is one relation that will be helpful. So a simple example is like if you are considering methane, say C1H4. So here X is nothing but 1 and Y is nothing but 4. So your A will be nothing but 1 plus 4 by 4. It is nothing but 2. So you can directly use this. So you need 2 moles of O2 plus 3.76 times N2 for complete combustion of the CH4 component, 1 kilomole of CH4. And another important reactions that were taught you was regarding with hydrogen and all. where you so I will just write it out. So you had a reaction like H2 plus A moles of air. So please remember that you don't get confused. Sometimes you directly use O2 when people say air and all. So you should be considering this 3.76 times N2 also. Don't get confused with that. So you have water that is coming out and A by 2 times of nitrogen. Here you don't have carbon at all, so X is 0 and Y equal to 2 you have. So your A will be 0 plus 2 by 4, which is nothing but half, that is 0.5. So you need 0.5 moles of air for 1 mole of 1 kilomole of hydrogen to get complete combustion happening. So these are some stuff that you need to remember in stoichiometry theory. And said that, so one another important term that you need to remember is something called stoichiometric air fuel ratio. This is important because this is what we say as a control parameter in combustion systems or in rocket engines or gas turbine engines. So gas turbine is nothing but the engines that are used for airplanes and all this stuff. So these air fuel ratio, that is stoichiometric air fuel ratios, which eventually in further lectures we will see something called equivalence ratios. So these are our control parameters. These are the things that change as your system is progressing from one particular state to another state. So stoichiometric air fuel ratio is calculated as mass of air required mass of air required to completely burn one kilogram of fuel. So that's the definition of stoichiometric air fuel ratio. So you might have watched in the lecture about the methane and all this stuff. I'm not going in detail for that. Then said that the other important term that you need to remember is equivalence ratio. So equivalence ratio is represented by phi. It is defined as the ratio of stoichiometric air fuel ratio to actual air fuel ratio. So this is the ratio of stoichiometric air fuel ratio to the actual air fuel ratio. So if your equivalence ratio is less than 1, that means we have more air is supplied than the theoretical air. More air is supplied than the theoretical air. Similarly, if your equivalence ratio is greater than 1, it implies the opposite one, that is less air is supplied than theoretical air. So said that, so for a case of N-heptane was shown in the lecture where you have C7 H16 was there, and from the theory you know 1 kilomole of heptane, that is nothing but X equal to 7 and Y equal to 16. The amount of air, that is A, is nothing but X plus Y by 4 is what we saw. You have 7 plus 16 by 4, which is nothing but, so you need 11 kilomoles of air for complete combustion of N-heptane. So 11 kilomoles is required from the theoretical thing that you came to know. Now, if you have say C7H16, but it is combination with very higher amount of air flow rate, that is O2 plus 3.76 N2, if you see, what changes happens is the output products. So you will now have carbon dioxide, water, since these two will be coming out because complete combustion is over, but you still have more air present in your system. So then you will have an excess amount of oxidizer O2 coming out and some amount of nitrogen released. Now is the same case, but now if you are putting lesser amount of air, so only 9 moles of kilomoles of air if you are using. Now the products, how it changes is, you have say some A amount of carbon dioxide coming, some B amount of carbon monoxide will be coming, because carbon dioxide by itself is not so stable. It decomposes into carbon monoxide, and then you can have water H2O plus H2 coming out plus some 33.84 times of nitrogen released. So this is the difference that you will see when you are dealing with lesser amount of air flooded and complete combustion is not, if it is not happening. You will not see O2 here because O2 is being completely getting combustion. So you will have some amount of H2 being released here. So it's an incomplete combustion and it occurs with carbon monoxide and hydrogen. So you may know carbon monoxide is a pollutant and people try not to get this thing out. So finally, we use some chemical equilibrium theories to understand this. So here you saw there is some A moles of carbon dioxide and B moles of carbon monoxide. So to calculate the values of A or D in this particular equation, we use a concept called chemical equilibrium, which will be dealt in detail in the second week lectures, and this is based on nothing but your second law of thermodynamics. So which is nothing but at a given pressure and temperature, a parameter called equilibrium constant, there is nothing but a Kp, is evaluated at a given temperature using Gibbs law of energy, or Gibbs free energy usually said. So this is number G minus H minus Ts. So these are applied to something called elementary reactions. Now there are two different things. One is called elementary reaction, one is called global reaction. An elementary reaction as opposed to a global reaction is a, so global reaction is what we said in a one-step reaction, what we wrote. Elementary reaction is between elementary atoms that react with individual. So an elementary reaction as opposed to a global reaction is a reversible reaction. So elementary reaction you can have say CO2 where you can move and come out with C plus carbon monoxide plus half moles of oxygen if you have. You can get carbon dioxide, or carbon dioxide can decompose into carbon monoxide plus half times of O2. Some similar examples is like you have water. This can decompose into H2 plus half moles of O2. And another important is carbon monoxide plus water. There you have a reversible reaction with carbon dioxide and hydrogen. So these are some elementary reactions where you can see these are represented as reversible. You can go in both directions. So these are elementary reactions, and you will further in upcoming lectures you will see how these reactions are used in finding particular adiabatic flame temperatures and all different things you will be learning. Yeah, so we are very close to the first one now. So these are the important things that were taught to you in the first week videos that you have received. Are there any questions? Yeah. So I hope you remember or at least recollect all the stuff that we have taught to you. So with this knowledge, we will move on to solving some questions that I have here. We will see we can solve them. we need further theories to deal with it. So we saw what are different fuels and their properties, and we saw a review of basic thermodynamics and ideal gas mixtures and all this stuff. Then stoichiometric things we have started. Eventually, in the next upcoming lectures, we will see more of the thing. Yeah. So the first question that I have is major fuel components of syngas are. So, have you heard of syngas? Yeah. No. Okay, so you can answer if you know the answer to this question. So the question is major fuel components of a syngas are. Is it carbon monoxide and oxidate, or carbon monoxide and these two carbon dioxide, or carbon monoxide and hydrogen, or carbon monoxide plus methane, which could be the major fuel components of a syngas? Does anyone have any guesses? You can just guess it. It's not any exam or anything you don't need to be afraid of. You know? So if I show you the answer, so the major components of syngas, so it involves carbon dioxide. By volume, it has a 2.1% of carbon dioxide, and it has by volume carbon monoxide in percentage of 18.8%. You have carbon monoxide, and you have hydrogen, which is by percentage volume as 28.3%, and you have nitrogen, which by volume is about 50.8%. So the main gross heating value or the calorific value of a syngas is close to say 6 megajoules per liter. So now can you guys say what is the major fuel components of syngas? What are the major components that we see here? Apart from nitrogen, you don't need to consider. What are the next two components of a syngas that are major in this? You guys will pick up. Okay, so you don't need. So this session is for problem solving session. So this is to help you in your assignments and all. So you can freely interact with it. So from this thing you can see the first major component is hydrogen, and the second thing is carbon monoxide. So you have carbon monoxide and hydrogen. So your correct answer will be H2 and C. Yeah, that's correct. Now, if we move on to the second question. So the second question is volatility of a liquid fuel depends on. So you can see there is a boiling water thing that we have shown, and there is some other liquid that is being used where you can see the fumes coming out as they are pouring up into the flask. So the question is volatility of a liquid fuel depends on. It depends on the density and isothermal compressibility of the fuel, or boiling point and latent heat of vaporization, surface tension and viscosity, or freezing point and turbid point. What is the thing that is dependent volatility? We discussed it a few minutes back. So you guys can try out what would be the answer to this. Volatility of a liquid fuel depends on what is the answer you guys think? Give guesses also. Just don't want to speak up. Okay. So for a liquid fuel, density is important. We saw. But isothermal compressibility is nothing but density with respect to pressure. So if it is important, so we didn't see any isothermal compressibility issues while we were considering. Yeah, so what is triple point? So triple point is nothing but you have say three phases. So you have liquid, vapor, solid, liquid, gas. So for water you have a triple point at say some 273 Kelvin or something for a given pressure or some value. So at this point you have a coefficients of solid, gas and liquid present. So that's what we call as triple point. You can see the gas phase diagram of a water. So you will see there is a solid line. Within this region you will see solid ice being present. Then here you will have liquid water and you will have here steam or the water vapor. So this particular thing is what, so that particular point where the coexistence of all three happens is what is usually called triple point. But do you think volatility of a liquid depends on the triple point? Or it depends on the freezing point? Or does it depend on the surface tension and viscosity? So this, we discussed the theory and a few minutes back. Any guesses? What could be the answer? Just try it out. No, don't worry if it's wrong or correct. You can type your answers in the chat if you are not ready to speak. Boiling point and latency. Yeah. So yeah, that's correct. So your volatility usually depends on the boiling point and it depends on the latent heat of vaporization. So as I said, latent heat of vaporization is depends on your the amount of heat that is required for the phase change, and boiling point is the saturation temperature corresponding corresponding to a given pressure. When what is the saturation temperature? That's what we call boiling point. And based on these two things is what volatility depends on. So how much vapors you will get from this. So in the figure here on the right you can see it is bromine, which is a dense liquid with a melting point of -7 degrees centigrade and a boiling point of say 58.9 degrees Celsius. So you can see this bromide being, so it's so volatile that you will see vapors when you are pouring itself, you will see this stuff, vapors being coming out of the flask. So that's the stuff there. So volatility of a liquid fuel depends on the boiling point and the latent heat of vaporization. So that was the second question I had. Then the next question is, what calculate the number of moles of standard air in kilomole. So what is the number of moles of standard air that you have, and they are asking in kilomoles how much is the value. This I think you can try it out. It's not a, we have discussed so many times in the previous few minutes. So what could be the answer? Is it 4.76 number of moles of standard air, or 3.76, or 1 kilo, or 3.4? We already, so for you a given hint is, we said that nitrogen is 78%, nitrogen is percent and oxygen is 21%. Remaining gases are all say 0.4% or other gases. So with this, in terms of by volume, if you know this percentage, what is the number of moles of air that you have? Yeah, wait for 1 or 2 minutes. You guys can try it and let me know in the chat what is the number of moles of standard standard air in kilometer. I'll wait up to say 8:40. You guys can try it up. Okay, so we're gonna do the same 3.4 moles of standard air is present. So we look into it. So a standard air. So as you can see here, we have 78% of nitrogen, 74. So we approximately to say some 79% of nitrogen we have, and the remaining will be 21% of oxygen that we have. So by volume, if you see, so the total number, so the total volume that you have, say 100% is nothing but 79% you will have nitrogen, and 21% will be having oxidizer. So if you see here, so you will have O2, say some amount of O2 you will have, and some amount of nitrogen you have. So this whole thing is what you call as air. Now the number of moles of oxidizer and number of moles of nitrogen is what you need to find it out. So if you are considering oxidizer at 21% by volume if you are having, so say if A is equal to 1, then we have 1 kilomole for oxidizer. How many moles of nitrogen is required? So you have 79 by 22. So this comes close to say some 3.76 kilo, 76 kilo. So that means your B is nothing but 3.76 kilo. So in total, if you see, you have 1 kilomole of oxidizer plus 3.76 kilomole of nitrogen. So this is what you call as air. So here the question is, what is the number of moles of standard air in kilometer? So what is the total number of kilomoles we have? It is 3.76 plus 1. So in total you have 4.76 kilomoles in a standard air. So in a standard air you have total 1 kilomole of oxidizer plus 3.76 kilomole of nitrogen. So you will have total 4.76 kilomoles present in a standard air of say your substance or a gas, a oxidizer and nitrogen in standard air. So your answer should be 4.76, not 3.76. So I hope you understood how we calculate it. So if we move on to the next question. So the question is, the molecular weight in kilogram per kilomole of biogas having 45% carbon dioxide by volume is around. So we are asking you to find the molecular weight of biogas which is having 45% carbon dioxide by volume. Let's try it out. I will wait for say 2 minutes, 2 or 3 minutes for you to try it out. biogas here. What is the molecular weight? Yeah, that's right. Here we have 28.6 kilogram per kilomole. So how we calculate it? So we have say 1 kilomole. Right. So for 1 kilomole, say you have 100% of carbon dioxide you had into if you had into it. Now here they are saying you have 45% of total carbon dioxide is present. So that means you will have 0.45 kilomoles of item being present. So for a 0.45 kilomoles of carbon monoxide, to calculate the molecular weight, number of moles into the molecular weight of CO2 unit to C. So 0.45 times. Carbon has a mass of 12 grams plus oxidation or oxygen has 16 as its value, and you have two sets here. So it will be 0.45 times 12 plus 32. So this is nothing but 0.45 times 44. So if you multiply it up, you will get a value of 28.6 kilogram per kilomole. So this will be your molecular weight of biogas, which is having 45% of carbon dioxide. I hope that is clear. If we move on to the next question. The next question is the calorific value of biodiesel is dash than of a fossil diesel. Fossil diesel or general diesel that we have. The question is the calorific value of a biodiesel is dash that of a fossil diesel. So if you remember biodiesel, how we have discussed a few minutes back in the first hour. So the calorific value of a biodiesel, is it greater than fossil diesel or lesser than or exactly as same as fossil diesel or not compared as such? What could be the answer? You just think of and let me know. Fossil diesel is something that your regular diesel that you get from the world. Yeah, so lesser, yeah, that's right. So the calorific value of a biodiesel that is derived from the alcohols and all is lesser than that of a fossil diesel. That is your thing. And important thing, if you see the figure that I have shown you can see a renewable diesel, that is a biodiesel. It has much lesser fumes compared to a fossil diesel that produces as a lot of amount of carbon coming out and incomplete combustion happening here. So fossil diesels have much more lot of other components that are being generated due to incomplete combustion happening. And there are renewable diesels. So that's why people try these renewable diesels because they are more their combustion is happening more clean and we are not getting these high fumes and smokes related to the renewable diesel. So that's some additional information that I picked for you. So the answer to the question is that calorific value of a biodiesel is lesser than that of fossil diesel. And if you check it out if anyone has any questions. Now, if we move on to the next question. So the next question is, anthracite coal has fixed carbon in the range of 85 to 95 percentage carbon, or 76 to 82 percentage of carbon, 92 to 98 percentage of carbon, or 65 to 70 percentage of carbon. So it's important that you know what is anthracite coal. So that's why I have kept this question. And there is some specialty for this anthracite coal. So the question is, anthracite coal has a fixed carbon in the range of, what could be the range of this? Is it 85 to 90, or 76 to 82, 92 to 98, or 65 to 70? There are different coals available, but some areas, the coal has also different grades, but anthracite coal is something that has a peculiarity. You can just wait for 1 or 2 minutes. You can just think of what it could be. And just let me know. Yes. See for 1 minute. So, so this is the picture of anthracite coal. It's number 11. So the anthracite coal, the peculiarity of anthracite coal is, anthracite coal has the maximum percentage of carbon. So it has close to 92 to 97 percentage of carbon percentage. So that's the coal that has the maximum carbon percentage. So that's the peculiarity of anthracite coal. And remaining, you have hydrogen of close to 1 to 3 percentage, and remaining oxygen, nitrogen, and all will be having. So your correct answer will be 92 to 98 percentage of carbon percentage includes, is present in an anthracite. So as you are doing the fundamentals of combustion course, you should know a regular coal that being used in several industries, in gas power plants, thermal power plants, and all. Why people choose anthracite coal, or why they don't want anthracite coal? One peculiarity of that is the carbon percentage. That is 92 to 97 percentage. So it has a very high percentage of carbon. So you need more amount of oxidizers for getting more complete combustion, else you will be getting carbon left out in your products, and you will get what we say soot formation, and much more things coming out if you are having a large amount of carbon present in the system. Yeah, so I hope you can look into it more. So that was that question's answer. Now the next question is, the mass percentages of moisture, volatiles, fixed carbon, and minerals in a solid fluid are obtained by proximate analysis, alternate analysis, volumetric analysis using gas chromatography, or both A and B. This we have just mentioned it in the previous few minutes. But in the lecture videos you might have learned this. What is the if you want to segregate the mass percentage of moisture, volatiles, the fixed carbon and minerals in a solid fluid. So you have a solid fluid and we showed you that there are four different components in a solid fluid. Initially you have moisture. If you are heating it up, you get moisture out. Further you are heating, you will get the volatile gases coming. Then you have fixed carbon left out and the minerals that burn down to ashes. So which analysis method is used to do this stuff? And this is being discussed in the lecture video first. So I'll wait for some 1 or 2 minutes for you guys to give me a guess answer. Think of what we mentioned or what was the analysis technique that we mentioned during that solid fluid discussions. Give a shot to the answer. Yeah, so that's right. So you have what we mentioned as approximate analysis. Where you get SR term is not available in market. Yeah, you can just search in Google SR terms PDF. You'll get if you want a PDF, if you want a hard copy, I think Amazon is selling that SR terms. You can directly get a PDF of the textbook from the online. So the question was mass percentage of moisture, volatiles and fixed carbon and minerals in a solid fuel are obtained by approximate analysis. So that's the analysis method that is used for separating out the moisture by heating it up. Then after heating you will get the volatiles out. Then the remaining fixed carbon and the minerals in the solid fuel are obtained using the approximate analysis. Gas chromatography and ultimate analysis gives you the percentage of products compositions. So that's different. So approximate analysis is what we use. So the next question that I have, what is the value of specific gas constant in kilojoule per kilogram Kelvin for a gas having a molecular mass of 44 kilogram per kilo? units that you are working with. It is being asked in kilojoule per kilogram Kelvin. So when you are finding out the value of universal gas constant, so say this definition for specific gas constant is nothing but universal gas constant that we mentioned as RU in this thing. So RU divided by the molecular weight of the mass. Yeah, that is. Yeah. So here, universal gas constant RU is nothing but 8.314. It should be 8.314 kilojoule per. If you are writing it in joules, then it will be what written here. But since it is asked in kilojoule per kilogram Kelvin, so you can directly write 8.314 joule per mole Kelvin divided by the molecular weight of the gas. It is given as 44 kilojoule per kilogram per kilogram. So here you have a kilometer at the bottom. So this will be coming to, yeah, now it's what here. So 8.314 into 10 to the minus 3 joule per mole Kelvin divided by 44 here, and the unit will be kilogram per mole. So now if you equate it, so it is 8.314 into 10 to the power minus 3 by 44. So the moles will get cancelled and you have kilogram joule per kilogram Kelvin. You have a Kelvin. And now if you divide it up, you will get a value of 0.1889 kilojoule per kilogram Kelvin. Your second answer is correct. So 0.1889 kilojoule per kilogram Kelvin is correct answer. So I hope you understood the concept well. Now, said that, the next question I have is specific heat at constant pressure of an ideal gas is mathematically defined as. This we just discussed. So the specific heat at constant pressure is what they are asking. This is the key thing. At constant pressure of an ideal gas is mathematically defined as. This is defined as dH by dt or du by dt, dE by dt or Tds. So I'll wait for 1 or 2 minutes. This we have just a few minutes back we have asked. What is the specific heat at constant pressure? What is the specific heat at constant volume? You guys can try it. Okay, so H here refers to the enthalpy. U refers here internal energy. And E refers to the total. And T is temperature and S is direction. So now, which one do you think is specific heat at constant pressure of an ideal gas? Yeah, so that's correct. So enthalpy is what you measure at a constant pressure. So the specific heat Cp is nothing but dH by dt, that is the constant enthalpy will get, whereas constant volume is what you would say as du by dt, that is internal energy. specifically at a constant pressure of an air. So mathematically it is defined as Cp into dH by dt. So that is what we have shown. So A is your correct option. I hope that is clear. Now we will move on to the next question. So the next question we have is molecular mass of a stoichiometric mixture of methane and oxygen in kilogram per kilomole is. So they are asking you to find the molecular mass of a stoichiometric mixture. So I'll wait for some 2-3 minutes. You can try it out. They are asked to find the molecular mass of a stoichiometric mixture of methane and oxygen. One answer I got is 32. So we'll see how to do this. So they are asking you to find the stoichiometric mixture of methane and oxygen. So you have initially methane and you have oxidizer gas. So on the stoichiometric mixture, we consider it as theoretically complete combustion is happening. So your outlet products should be carbon dioxide and water completely. So you are not neglecting all the smaller things. Now with this thing, so initially we don't know how many moles are there. So I say A moles of oxidizer I used. So I should get B moles of carbon dioxide plus say some C moles of water vapor I should get. And I have 3 elements here, carbon, hydrogen, oxygen. And I have 3 unknowns here, A, B, C. These are 3 unknowns. So for solving 3 unknowns, you need at least 3 equations. So I have 3 components here, carbon, hydrogen, oxygen. So I can get 3 equations from the equation that is above. How will I write the equation? For carbon, if we see, on the left hand side you have 1 carbon atom, which is equal to, on the left you have B carbons plus, so you have only B carbons here. So that means this implies B is equal to 1 you already got. Now for hydrogen, on the right hand side you have 4 molecules, 4 atoms of hydrogen you have, 4 atoms of hydrogen you have. On the right hand side you have 2C. So this implies C is equal to 2. So you got C, you got B. Now you need A. So for oxygen, if you see, it has 2A on the left hand side, and oxygen on this right hand side is 2B plus C. And so A is nothing but 2B plus C by 2. 2 into B is nothing but 1, and C is nothing but 2 by 2. So it is final equation that you have is A, the coefficient A is 2, B is 1, C is 2. So your final equation, the stoichiometric equation will be CH4 plus 2O2, that is A you report as 2 moles of kilomoles of O2 will give rise to 1 mole of carbon dioxide, that is B is equal to 1, and 2 moles of water, so that is C is equal to 2. So now you got this stoichiometric equation. So this is your stoichiometric equation at your hand. Now you need to, they are asking you to find the molecular mass of the stoichiometric mixture of methane and oxygen. So what we have, so the for methane, this is your, so what is the molecular mass of methane? Carbon is 12 plus hydrogen 1, and we have 4 of them. So this is your 16 kilogram per kilomole. And the next component that we have is oxygen. O2. O2 is nothing but 16 is its molecular weight, and you have 2 of them. So you have 32. Now O2 is 32, but you have 2 moles of O2 for the stoichiometric case. So you have 2 into 32. This is nothing but 64. So you have 64 kilograms per kilomole. Now they are asking you to find the molecular mass of the stoichiometric mixture of both methane and oxidation. So you need what you need to sum it up. So you have 64 plus 16, which is nothing but, so this is in, say, in kilogram if you are taking, because here it is asked for in kilogram. So you will have 64 plus 16, that is nothing but 64 plus 6 is 70 plus 10, it is 80 kilograms you have. And so how many moles, this is per, this, how many moles you have? The question is asked for kilogram per kilomole. Per kilomole, what is the value they are asking? So this 80 kilogram is for 3 kilomoles of product, 3 kilomoles of reactants, that is 1 kilomole of methane and 2 kilomoles of oxidation. So you have 3 kilomoles, 80 kilograms. So for, and you are asked in kilogram per kilomole. So that means you have 80 by 3 kilogram per kilomole is your molecular weight. So this 80 by 3 is nothing but 26.67 kilogram per kilomole. So you have this much, this will be the molecular mass of the stoichiometric mixture of methane and oxidizer in kilogram per kilomole. So I hope you understood what was the, so these questions are simple, but you need to be taking care of what is the units that you need to be taking out. So here the answer is 26.16. So the important thing is what is the units you need to be careful about, and what they have asked. So you need to properly read the question and answer that properly, so that you don't make mistakes when you are doing your assignments. So I hope that is clear. Yeah, so we have reached the end of the questions that I have. So does anyone have any questions regarding the assignments here, or the theory that we discussed in the first half? Yeah, so in short, we saw water, fuel and their properties. We saw, we had a review of basic thermodynamics, the properties that you have, ideal gas equations and all. And then we saw some basics of stoichiometry. Now next we will move on to first and second laws in the second lecture, second week videos in the first and second law of thermodynamics. guys have any questions. So I hope this will help you in solving your assignments. Okay, so I will wait for 1 or 2 minutes for if anyone of you have any questions to ask or else we'll meet in the next Saturday with week 2 session discussions. Thank you. So what is the difference between a molecular mass and a molecular weight? So there is a simple difference is like mass of a system will not depend on your gravity, G value. Whereas when you are saying weight, it depends on your G. What is it? So your mass on moon and earth will not change because it is not dependent on your gravity value. But as weight, it depends on gravity. Weight is nothing but m into G, whereas mass is nothing but m. So when you are saying molecular mass, it is in kilograms. Whereas when you are saying weight, it is in kilogram into meter per second square. So there is a difference here. So when you are asked molecular mass, you should be saying it in kilograms. And since here they have asked kilogram per kilogram, we change it. But this is the basic difference between mass and weight of a given system or molecule or anything. So I hope that is clear. What is the basic difference between mass and weight? Is that clear? Can I get the written notes that you taught today? Yeah, so IIT Madras team will be sending you an Excel sheet. Molecular weight and the same unit. No, so molecular mass, as I said, mass is in kilograms and weight will have a different unit here. But when you are dealing with molecular weight and all, weight, we say it in grams, but usually it is molecular mass what we are talking about. Because we say only in grams and all. We don't consider gravity stuff. So usually we say molecular mass, and what we are saying in molecular weight of a substance is the total weight that it has. That is given for each particular item. Carbon has 12, which is all predefined thing. So that is what, that total thing what we say is molecular weight. That is carbon dioxide has 44 as its molecular weight. So this particular stuff involves all the things that I have mentioned. So 44 involves all the 12 plus 16 plus into 2, which individually involves all the weight considerations and all, considering it is in air, atmosphere and all these things. So it is being weighed based on atmospheric conditions. But it's a terminology that people even common countries, but for our subject and all the disciplines, molecular weight or molecular mass when we are saying, molecular mass is particular element, if you say it's 12 grams for carbon dioxide, sorry, for carbon, and for a compound we say molecular weight where you have carbon dioxide which is a 44 grams. Yeah, then your first question, Vedant's question was, can I get the written notes that you got today? Yeah, so my trust team will be sending you an Excel sheet where you can click on, you will be getting Excel sheet with links to the video. This will be posted on YouTube. So you will get the links to that, and you will have a Google Drive file link also in that, where you can click and you will get all the things that I have taught today. Is it costly to purchase from store? Yeah, so I think SR terms is a bit costly in the sense cost depends on, for different people it is different. But if you look at the book online, a bit costly. I think you will get curious on it. Look to it if you are not getting just so in your Swayam portals you have a discussion forum there. You just post your if you are not getting you just post on the discussion forum. So your hardcover copy it shows 44,000 in Amazon. It's a bit costly. So you can put a request there. If you are not getting a PDF, we will try. We'll see if we can get a PDF and we can update. So in your Swayam portals you have a discussion forum. You can just post it. We will. So you have your login ID and password for getting into your course details in Swayam portal or NPTEL portal that you have. So there on the top you will have discussion forum or discussions and Q&A box, Q&A thing. There you can ask and we can do it. If it's needed, we will try it. Are there any more questions? I will wait for 1 or 2 minutes. If no more questions, we are done for today. Have a